Hi everyone, my name is Yuzhe Fu. I'm currently a master student at Shenzhen Graduate School, Peking University. Today I'm going to present one of our most recent works, an energy-efficient 3D point cloud neural network accelerator with efficient filter pruning, MLP fusion, and downstream sampling. Nowadays, point cloud is easy to be obtained with high resolution and efficient data format. It has become an important modality for deep learning tasks such as classification and segmentation. Also, point cloud is widely used in various applications such as driving and mixed reality. Unfortunately, point cloud is disordered and insensitive to rotation, which makes networks hard to extract its features. Therefore, point cloud neural networks are developed. PNN. PointNet is like AlexNet in PNNs, which overcomes the disorder problem by using multiple MLPs and max pooling layer. And the input transform and filter transform operations are used to solve the rotation insensitivity problem. Then the sampling and grouping operations are introduced in PointNet++ network to extract better local features. The residual structure is introduced in PointMLP network. Recently, the PointNext use a new training strategy and adjust the residual structure, which achieves the best performance. Therefore, we use PointNext as our benchmark. Let's focus on the architecture of PNNs. It usually contains several stages, and each stage contains a mapping layer, several consecutive MLPs with 1x1 kernel size, and an aggregating layer, which is usually the max pooling. The mapping layer contains sampling and grouping operations and aims to build a relationship between the input and output points. After mapping layer, the features of input points are grouped, which are convolved through consecutive MLPs and get the output feature group. Then the aggregating layer is performed and get the output features. Here is the architecture of the PointNext network as an example, which has 5 stages. But the memory bandwidth and the computation bottleneck will limit the hardware acceleration of PNNs. The low data reuse in MLPs for 1x1 kernel size with large parameters in PNNs would cause large amount of off-chip memory access. And the grouping and the sampling operations lead to irregular indexing patterns, reducing the memory access efficiency. For computation bottleneck, the convolution dominates in computation and storage, causing high complexity, and the sequential operation in FPS leads to low parallelism and non-latency. For existing works, Masorasi proposed a delayed aggregation method to increase the feature reuse, but it changes the order of operations in PNNs and it degrades the network accuracy. PNNPU proposed a block partition and a predict method to reduce the irregular memory access. However, the proposed blocking method cannot perform well in small-scale scenarios. A configurable PNN accelerator, PointACC, is proposed to support multiple types of PNNs. However, the off-chip memory access is large. To address these existing challenges, we proposed an energy-efficient and low-latency PNN accelerator for real-time 3D point cloud inference with 3 main contributions. An efficient filter pruning strategy is proposed to skip the redundant filters and activations in network. A blockwise MLP fusion method is proposed to improve features reuse and reduce off-chip memory access. Finally, to address the high latency and complexity issue of FPS, a downstream blockwise FPS method is proposed. Let's focus on the efficient filter pruning first. In PNNs, the convolution operations still dominate the computation data storage, which brings high energy consumption and non-latency. Second, unstructured element sparsity of quantized PNNs is not friendly for hardware acceleration. To solve this, we discovered 3 characters in PNNs. First, since the contribution of different filters to the network accuracy varies greatly, some less important filters can be directly pruned without accuracy loss. Second, in the MLPs of PNNs, the filters are reused in only 1 dimension across features, rather than in 2 dimensions such as 2D CNN. Therefore, in PNNs, a greater number of filters can be pruned with minimum impact on the network. Additionally, The pruned filters in the current layer can also introduce sparse channels to the next layer's input feature and filters, which increase the channel sparsity of both features and filters. Based on this, the filter pruning is efficient on PNNs. We performed the EFP on Pointnext network with a 78% overall filter pruning rate. The improvement is significant. EFP brings a lot of channel sparsity in both features and filters. As a result, the computational complexity and the model parameters are reduced by 12.4 times and 29.2 times respectively. And the output stationary data flow of the proposed accelerator provides strong support for structured pruning, resulting in minimum hardware overhead. The next part is blockwise MLP fusion method. In PNNs, the grouping operations can enlarge features by k times, causing much larger feature size than filters. The on-chip feature reuse is slow due to the 1x1 kernel size of MLPs, and the conventional data flow, only the entire features of current MLP are convolved, the next MLP would begin. So all of this would cause low hardware utilization and large off-chip memory access. We noticed that in PNNs, the multiple MLPs are consecutive. Therefore, the features can be reused across MLPs. What's more, the 1x1 kernel size of MLPs enables direct partitioning of the features without a complex padding processing. Based on this, we propose blockwise MLP fusion method. To begin with, the filters are pre-stored on-chip by fusion. For each stage in network, BMF partitions the input features into feature blocks, which are calculated through entire stage to get a stage output block. Consecutive MLPs enable the reuse of features in form of feature blocks. In hardware implementation, a feature block data flow loop is built between the memory module and the convolution module, enabling the on-chip reuse of the feature block across MLPs. As a result, a 21.1 times off-chip memory access reduction is achieved for Pointnext S with BMF. The effectiveness is contributed to two aspects. First, EFP reduces the size of both filters and features, enabling them to be stored on chip. Secondly, the block partition operation in BMF enables the off-chip memory access of the large grouped point features. Therefore, no need of off-chip memory access during stage process, and the BMF also improve the hardware utilization. Now, the next section is downstream blockwise FPS method. The original FPS processing is sequential with a high computational complexity, making it become the latency bottleneck, and the irregular memory access of FPS worsens the latency. We propose a downstream blockwise FPS to solve the problems. There are two steps in DSBF: downstream prediction and downstream partition. In downstream prediction, two distinct sparsity strategies are adopted to reduce the original input points into two small sparse sets. Then FPS is performed on each set. After point counting and scaled, the results are accumulated to get the predict values, which are used in the second step. In downstream partition, the input point cloud is spatially partitioned into cubes firstly to maintain the global feature of point cloud. Then each cube is evenly sampled into two blocks to improve the parallelism. Based on the predicted number from the first step, these blocks are performed FPS separately and get the final result. When partitioning the point cloud into 16 blocks compared with original FPS, the proposed DSBF reduces around 14 times computational complexity with few network occurrences. Compared with the NPU, in the distribution of numbers of points among blocks, our red line on smaller MAE and is more similar with the green line, which is the original FPS, and will achieve 1.91 times higher network occurrency with similar computational complexity. The system architecture of the proposed point cloud accelerator is introduced in this slide, which consists of a control module, a mapping module, a convolution module, a pooling module, a memory module, and an inference module. The memory banks can be dynamically allocated to meet various bandwidth and storage requirements of other modules. An instruction set architecture is designed for the off-chip host to control the accelerator. For evaluation, the proposed accelerator is implemented in the TSMC 28nm CMOS technology. Cadence Genius is used for synthesis and power evaluation. The benchmark is the 8-bit PointNeXT network classifying ModelNet 14 dataset. This is the area and energy breakdown of the proposed accelerator. The total area is 1.46 square millimeter and the power is 0.13 millijoule per frame. We achieve 12.65 TOPS per watt energy efficiency. So compared with the baseline, we achieve totally 15.32 times speed up and 13.6 times energy efficiency improvement. The proposed accelerator is compared with the state-of-the-art accelerators. We achieve up to 66.6 times higher energy efficiency, 70.2 times lower energy consumption, and 74.9 times higher overall efficiency. So finally, I would like to conclude my talk today. An energy-efficient real-time PNN accelerator is proposed to reduce the high energy consumption and non-latency caused by convolution. An efficient filter pruning is proposed. A blockwise MLP fusion is proposed to increase the on-chip reuse of features and significantly reduce off-chip memory access of point features in MLPs. Then, to eliminate the latency bottleneck of sampling, a downstream blockwise FPS method is proposed to enhance the parallelism of sampling while maintaining the inference accuracy. Benchmarked with the PointNeXT network, the proposed accelerator outperforms the state-of-the-art works and achieves up to 66.6 times energy efficiency improvement. Thank you for listening.